Okay, maybe we should just get started so we don't lose too much time. So we're going to continue talking about our ring homomorphisms, really looking at our first isomorphism theorem and getting more comfortable about how to use it. Actually proving it is not like the main focus, right? It does help us figure out like these smaller details with our quotient rings and feeling more comfortable with them. But really what I want us to take away is, when can we apply this? Why do we want to apply this? Does this actually make any of our work simpler? And we're going to continue on with our packet. At the very end, I said something like there's a preview into fields of quotients, which I wrote up a packet on, and I'm still trying to decide if we actually want to go through talking about this or if I'll just make this a handout that you guys can read if you're interested. The idea behind it is pretty interesting, but we're not going to use it very often. But maybe by the end of class, I'll have decided if we're actually going to go through this entirely or not. Okay, so let's look at our first isomorphism theorem and remind ourselves of what's going on here. So here, this is telling us that if we're given a ring homomorphism R to S, then we can find an isomorphism. The middle part is telling you what the isomorphism is, but it's really telling us that R mod the kernel is going to give us back the image. They're going to be isomorphic to each other. They're not exactly going to be equal. They can have different elements, but they really work in the same exact way here. Where our kernel, we saw, gave us back an ideal, and we found out that ideals really are the same as kernels. So as soon as I know something is a kernel, I know I can see it as an ideal. As soon as I have an ideal, I know I can see it as a kernel. And so here, our kernel is nice as an ideal, and so I do actually get a quotient ring back out, and it's going to be exactly isomorphic to our image here of our ring. So lots of times what we end up doing is, what we want to do is show that a quotient ring is isomorphic to something, and our goal is to find in a group, or a ring homomorphism, so that our setup works out nicely here. But most of the time what's going to happen is all you see is a quotient ring isomorphic to something, and we want to use the first isomorphism somehow to give us that info. And I think we have the setup for one of these here to make it a little bit easier to see. Okay, here I have a quotient, here I have a ring that I should feel comfortable understanding. So what you want to do is you want to fit the nice pattern of our first isomorphism theorem. So what you want is a map from the top part of our quotient, the big ring, to our ring, the simpler length ring that's not a quotient. Okay, and really because I want this to be the full image that's inside of my first isomorphism theorem, I need to come up with a ring homomorphism where this is surjective. It's not going to be enough to just be a ring homomorphism. I want it to be isomorphic to this whole thing, so it has to give me back the whole thing back out from my image here. Okay, so we'll make the domain the top part of our quotient. We'll make the codomain what we want it to be isomorphic to. We want this to be surjective in a ring homomorphism. And then on top of that, the last thing that we need is that the ring homomorphism that we find turns our ideal that we're modding out by in our quotient ring into the kernel. So the ring homomorphism that I have to come up with has to be surjective, and it has to give you back the appropriate kernel here. Right. So the hard part is going to be not the setup. This should be like pretty natural to figure out what pieces go where, but deciding what the ring homomorphism has to be. Most of the time, it's going to be something kind of natural. If we're working with polynomial rings into a simpler ring, usually we want to evaluate at a specific number. When we're working with like integers and mod n, here the natural thing is to take the integer and mod it by n to land in the correct place. But again, we need it to be a ring homomorphism, we need it to be surjective, and we need the kernel to be exactly what the ideal is that shows up in our quotient ring here. All right, so that's the setup. That's how we use our first isomorphism theorem, because otherwise what we'd have to do is come up with a direct isomorphism between the two rings, which can be pretty tricky to do. If you want to find a direct one, you can use the one that shows up in the first isomorphism theorem itself. But now it's just enough to show I have a surjective ring homomorphism where this is the kernel. First isomorphism theorem tells me these two have to be isomorphic to each other, or these two here that show up in our commutative ring here. Okay, and we did some more work on this, where we worked with the polynomial ring with real coefficients. And really, these polynomial rings are going to be a whole chapter that we'll study probably starting on Wednesday or Thursday. We'll have a full section kind of starting from the basics, even things that we've already seen, just to make sure that we have all of that down. And so here what we'll do, or what we did in this one, is we're already given a function, and the goal was to figure out how can I use the first isomorphism theorem to tell me which things are isomorphic to each other. So I need to find what the image is of this map. Turns out that it's surjective, so it's going to give me the whole codomain. And I need to find what the kernel is, so I know what to mod out by. So I'll take my domain, mod out the kernel. I should get back the image, as long as this is actually a ring homomorphism. So that's something that we have to check. And within that, we would have to check well-defined. This one turns out really nice because it depends on the function itself. The functions are well-defined. Regardless of where I plug it in, I should only get one answer back out. Okay, we check. We didn't actually check, but you can check that it preserves the operation or that it's a ring homomorphism. Instead of deciding what the image is, I actually told you to give you back the full ring. So we showed that it was surjective. And then we studied what the kernel was here to tell us if I take the polynomials with real coefficients and I mod out by this ideal generated by x squared plus 1, which is really the smallest polynomial in here that has I as a 0, I get back all the complex numbers. And really, my real numbers are just missing that I. As soon as I have I in there and I know I have a ring, I'm going to have all of my complex numbers. So this gives us a way to connect what's going to happen, or really put a light bulb in for us when we see this later on. When will I know that these are isomorphic? What happens when I quotient out by something that I know the zeros of and I know where they live? And so we'll get a lot more information about this kind of stuff in our next chapter on polynomial rings. Okay. Great. Oh, and I said this earlier, but we did talk about it, right? We already knew that kernels gave us back ideals, but now what we can say is that if I know I'm an ideal, I know I can show up as a kernel as well. So they really are the same. They just show up in different places. So I can think, given an ideal of a ring, I can see it as a kernel of a ring homomorphism where the domain is R. So if my ideal I is an R, I can come up with a ring homomorphism from R to something where I is going to give me exactly the kernel here. It turns out that the natural thing to do is to take R and map it into R mod I that I already know is a ring, and do the natural map that takes any element in my ring and sends it to the coset represented by that same element. And it turns out that my ideal is going to be exactly my kernel here. So this is how I can view my ideal as a kernel of some ring homomorphism where R is in the domain. Possibly I could have different maps here. I could have different codomains, but this is the natural one that we can always work with here. Okay, so again, we'll let I be an ideal of the ring R, and we're going to look at the map from R to R mod I. So since I is an ideal of R, R mod I does give me a quotient ring back out. So this is going to give me a map between rings where we want to send any representative or any ring element into the coset represented by that element. And our goal is going to be to show that we get a ring homomorphism that's surjective so that we can see, or I guess actually we don't even need that information. We just really need to know it's a ring homomorphism and what the kernel is going to be here. And it should give you back the full ideal itself. Okay, so if I want ring homomorphism, I first need to make sure that it's actually well defined. That if I take two elements in my ring R and I map them over, that I actually get the same output back. So starting at the same input, I should get the same output for well defined. But this one is a little bit more clear. So here, if I have R is equal to S in my ring, possibly I have multiple ways to represent the same element. So I really want to think maybe they look different, but they are the same element in my ring. Then I want to look at what do I get for their image. In my first case, I get back R plus I, the coset represented by R. Okay, but if R and S are the same element, they really do represent the same exact coset. And here I can even think R minus S is equal to 0, which I know is always inside my ideal. So that's how I can prove that these two things are actually equal to each other as cosets. And this is exactly what I would get if I plugged in S instead. So again, starting as the same inputs, the goal is to show that we got the same outputs as well. So R and S are equal. We wanted to show that phi of R was equal to phi of S here. And this one feels silly just because we already have pretty good understanding on our cosets. So if they're literally the same element, they should represent the same exact coset here is what we're saying. Okay, we need to show that it's a ring homomorphism. So we want to show if we add on the inside, it's the same as adding on the outside. If we multiply on the inside, it's the same as if we multiplied on the outside. And again, these are going to feel really natural by the way that we defined our addition and multiplication in our cosets. So for our quotient rings. Okay, so here we'll start with addition. And my math tells me, take whatever you plugged in and make that the representative for your coset. So you'll get R plus S plus U plus I. And my goal is to be able to separate this until it looks like phi of R plus phi of I. So here I want to remember when I'm adding my cosets, I'm really adding the representatives. So I can split these apart by splitting apart the addition that I see in my representatives here. And most of the time, we see it go in the opposite direction. We see the sum of our cosets and we simplify it, but we can go in the opposite direction as well. Okay, now this is exactly, this first one is the image of R, because I know R gets into R plus I, and then this likewise for our S. Okay, so here we were able to separate our sum. So when we saw addition in the inside, it's the same as the addition on the outside. Okay, and now we want to show multiplication, and this is going to look almost identical, except now with our multiplication, since we have a nice defined multiplication for our cosets as well. Let me just move this down. Okay, so here, if I multiply on the inside, I know my math tells me take this element and send it to the coset represented by that element. So R times S plus I. But I know how to multiply my cosets. I just multiply my representatives so I can split this apart. I get R plus I times S plus I. Just by our definition of multiplication for cosets. And now I can see these two individually are phi of R times phi of S. So again, these well-defined and then the ring or the preserving the operations feel very natural because we have a really good understanding of what our R mod I are. And this map here is a very natural map. I take an element from my ring and I send it to the coset represented by it. So it really doesn't feel like we're doing much here, but we are using our definitions of our operations to be able to move things around. Okay, and then the last thing we need to do is decide what is the kernel equal to. Right, because now I've shown I do actually have a ring homomorphism, and the goal is to show I is the kernel here, that I can see I as the kernel of some ring homomorphism, where R is the domain here. Okay, so here I need to think about things inside of my domain that get mapped to what? Right, my 0 element inside of my quotient ring. And so here that looks like 0 plus I. Okay, but I know exactly what 0 plus I is. I can represent that as just I. It's the same exact coset. Because if I take everything in an ideal and just add 0, I haven't actually changed any of the elements. So these are really all of the things in my ring. So that my output gives me back just the ideal. Okay, and then I want to think, what does my map actually do? My phi of R is exactly giving me back R plus I. So really what I need are all the R elements so that R plus I gives me back I. And how do I know that my coset gives me back the ideal I? Or what are some things that I can say because of this here? Right, and how do we know that this has to be inside the ideal? What facts about our cosets can we use here to say something about it? Right, we really should feel comfortable with these, but if we don't see it directly, we subtract the representatives here, and I really could have used my 0 plus I here. So here my representative is 0, here I have R, and the only way that these are going to be equal is if when I take their difference, they land back inside of I. So this is the same as saying the things in R, so that R minus 0 lands in I, but R minus 0 is just R. So all the things in the ring that are in the ideal, but because the ideal is a subset of the ring, it's going to give you the whole ideal back out. So your kernel really does give you back the whole ideal here. Right, and I could have done this like double containment, taken something in one and shown it's in the other, and then vice versa. But because we did equality of sets, we're done. We really did show that both sets were equal to each other here, right? Because all of these really were, if and only this, we will interchange these statements here. Okay, so here we can see that the ideal I shows up as a kernel of some ring homomorphism where R is a domain. So again, your ideals and your kernels, they really are essentially the same thing. We just gave them different names, or you can see them represented in different places here. Okay, so let's look at our next theorem here, which tells us about homomorphisms from integers to rings with unity. So here, if we let R be a ring with unity, and let's call that unity 1 sub R, and we're going to look at the map that goes from the integers to R, given by this specific mapping. So every integer is going to be sent to add 1 to itself that number of times. Right? This doesn't really mean multiply because I don't know that I have this element in my ring. This is shorthand for saying addition over and over again. So really I'm taking my integer, let's say 5, and I'm saying add 1 to itself 5 times. That's what 5 will be sent over to. Okay, and this is always going to give me back a ring homomorphism. Okay, so here we want to show that we do get a ring homomorphism when we do this. So we're going to let A and B be elements in our domain and our integers. And we're going to study what happens when we add these together. Okay, this is saying add 1 to itself R times. Add 1 to itself A plus B times. Okay, that's the same as thinking add 1 to itself A times, and then add that to 1 to itself B times. So we really can separate these. And this is exactly going to give me back C of A plus C of B. Right, because again, this is saying add 1 to itself A plus B times, which is the same as adding it A times and then adding it B times and adding those two together. Okay, let's think about what happens under multiplication. This one's a little bit trickier. All right, immediately this tells me add 1 to itself A times B times. And really what we want to do is to rethink, what do we mean by multiplication with our integers? when I do 2 times 3, what am I actually doing? I'm adding groups of 3, 2 times to itself, or I'm adding groups of 2, 3 times to itself. So really our multiplication is another shorthand for some form of addition, but now specifically just for our integers here. Okay, so here I can think, I can add 1 to itself a times. So add 1 to itself a times, and I want to do that b times, right? I'm taking this group of a, and I want to add it to itself b times. So this should be a times. This should be a times. Right, and in parentheses, these are really representing 1 being added to itself 8 times or 8 times 1, right? In each one of these that show up. And I need to think how many of these parentheses are showing up here. It's b, right? I could also interchange this. I can do these as b's, and then on the outside is all a's, but they really represent the same thing if I do a times b or b times a here. So in total here, I have this happening b times. So again, if this was 2 times 3, I'd be adding 1 to itself twice, 3 times. And 3 sets of these parentheses where I'm adding them twice on the inside. So again, just rethinking, what do we mean by multiplication? It's this repeated addition here. For our integers, yep. Yep, once we have things like 1/2 or rational numbers, they don't work as nicely, and really we're extending these definitions so that they work nicely with them. Okay, but this is going to give me back, right? I can really pull out this a times 1r to the front because it's showing up these b times. I really have this happening b times on the inside. So for everyone that shows up, I can pull out an a times 1, and I have a 1 left over. But then this is just a fancy way of saying add 1 to itself b times, so b times 1 here. Okay, and this is exactly giving us back phi of a times phi of b. A lot of this feels kind of silly just because this is how we think about our integers kind of naturally. So when I say add a to itself a times b times, I really can think of it as add a to itself, add 1 to itself a times, and multiply that by 1 to itself b times instead. But this is showing you like fully through how you can use your ring properties to move some of these pieces around. Because we don't know that this is surjective. This ring could be anything it wants. It just needs to have unity inside of it. So something like the real numbers would work here, but I don't necessarily get a surjection between the two. The real numbers are bigger than our integers here. What this is actually telling us, though, is that if this is injective, then you can see a copy of z inside of this ring here. Right? But we'll see some of those pieces showing up later on. Right, so instead you can think about z mod the kernel and think about what is that isomorphic to. It's going to be isomorphic to some subring of the ring R here. So you can use your first isomorphism theorem, now that you know it's a ring homomorphism, to make some more connections between the integers and whatever this ring is here. But the only property we need about the ring is that it has unity. So it's pretty simple. Like I don't need a lot about my ring to know that this is always going to give me a ring homomorphism back down. Question? So if I want to show something's a ring homomorphism, I have to show, I didn't do this, well defined, and then the closure of the two, or preservation of the two operations. So show that if I have addition on the inside, I have addition outside, which was my first one. And if I have multiplication on the inside, I should have it on the outside. It's unlikely that you'll see ones where it's defined in this way. Now we have this always is always going to be true. You don't have to check it for this specific type of map, right? So if I know that the map goes from Z to something with unity where it does this, now I immediately know it's a ring homomorphism. I don't have to prove it because this does it more generally for me. So we really want to think, when can we apply it? We can apply it when we have a ring homomorphism, excuse me, a map from the integers to a ring with unity, where this is exactly what the map is doing. Yep. So now we don't have to do this proof every time. We know that it's true as long as it's a ring with unity and it's this specific map here. Yep. Okay, so this gives us a couple pieces of information. Here we know that a ring is either going to have characteristic 0 or it's going to have characteristic bigger than 0, right? And if we have unity, it actually gives us a lot of information. And it just depends on what the unity's additive order is to tell us what the characteristic is. But here, if we have a ring with unity, so similar to what the theorem we had above, if we know the characteristic, and the characteristic is really just going to depend on what the unity is. So here, if it's some number bigger than 0, then that's telling us that we're going to have a subring isomorphic to Zn. So you can really see a copy of Zn living inside of your R. It might not look like 0, 1, all the way up to n minus 1, but it's going to work exactly the same. Where when you add them or when you multiply them, it works the same as in our Zn. When our characteristic of a ring is 0, then that's telling us that the ring is going to contain a subring isomorphic to the integers now. So here we will get isomorphism if I have more information about what the characteristic of the ring is. So really, we're going to apply our theorem and think about what are our choices for characteristic and what does that tell us about this map? Is it isomorphic? Do I have what my kernel is? What is it surjected into? What does the image look like? This is really going to answer those questions about how else can you apply this theorem here. Okay, so again, we're assuming we have a ring with unity. Okay, what we're going to do is we're going to look at the set S, where I want to add one to itself any number of times. So I really want to think here, take k, any integer, and add one to itself that number of times. And I want all of these possibilities. So I want 1, I want 1 plus 1, I want 1 plus 1 plus 1. And I also want to do this in the negative direction, so thinking inverses as well. Okay, so what this is telling me, 15.5 tells me here, I guess technically what we need to know also is that this does actually give me back a ring. If I just look at the things of 1 added to itself some number of times, actually, you always get a ring. My only issue here is, what if we don't get 0? What if the additive inverse of 1 is infinity? So I never get 0 here. So let's see if maybe we break this up into cases. But we can get a map here. Well, at the very least, we know that this is going to be a subset of R. Okay, but here, if I take the map that sends n an integer to n times 1, so the same map that we saw in our theorem, and we'll land in here, it's exactly what this looks like. So maybe I should really think, I really should have this going into R. And then we can think about what the image looks like depending on what this guy is here. But we do know that this map here is going to be a homomorphism. Okay, now we'll think about our cases depending on what the characteristic is, where the characteristic of our ring R just depends on what the additive order of 1 is. As soon as I know that I can go up to 5 and I'll get back 0, I'll get exactly 5 elements here. If I know that this has additive order equal to infinity, so I never get 0 back out, this is going to give me an infinite set back out here. Okay, so here, oh, that would give me 0 back out. So this solves a problem that I was thinking of earlier, that we don't necessarily always get 0 here, because when we think about order, we only think about natural numbers. So that was why I was not convinced that 0 would be in here. But as soon as 0 and negative numbers are allowed, I know 0 actually does land in here. So I actually can turn this back into S, because now I am convinced that this will give me a ring back out. But if I didn't have 0 immediately, I knew I did not have a ring in that case. So I can think here S, and this is a subset of R. Okay, but now this theorem that I had is showing me I do have a homomorphism, because now I am convinced this is a ring, and I'm using the exact map that we were working with here. Okay, and so now, right, this is actually going to give us more than a homomorphism. It's also going to be surjective. Right, it really can't go to anything else. It has to go to all the things that show up here. Really, that set is telling you what the image is supposed to be. Now I can use my first isomorphism theorem. And what does that tell us in our setting here? Now that I have a surjective ring homomorphism, what does the first isomorphism theorem tell me? What mod what gives me what? What? Phi of R, which is going to be our or phi of Z, because Z is our domain here. So it should be our image. But because it's surjective, what should I get back out? My whole codomain here. So here, because this is a surjective map, and it is actually going into S here, and this is a ring. This is telling me as soon as I know what the kernel is, I can tell you what the relationship is between R and S. And again, this should have been Z. This is supposed to be our domain. So we don't want to take it directly from our first isomorphism theorem. We want to translate all the pieces. So in our first isomorphism theorem, R was the domain. So here, our domain is Z. So anytime we saw an R in our first isomorphism theorem, we should replace it with Z. Mod the kernel is always going to look the same. Isomorphic to the image is going to change depending on what's going on. Here, because it's surjective, it gives us the whole codomain back down. But this is always going to be some subring of the codomain. Right? So that'll help you to remember and actually write that correctly. The R should not have been here because it was part of my codomain, not part of my domain. Yep.
It's part of
Yep, so it's going to give me back a subring of my codomain, but should be a part of my codomain. It could be the full codomain, though. Right? The full codomain is a subring of itself. Yeah. Okay, so we're going to break this up into pieces depending on the characteristic. It's going to tell us what these are going to be isomorphic to. Really, we want to show when the characteristic is bigger than 0, then R contains a copy of Zn. So really, this is going to be the copy that's in R. What would we want the kernel to be? If I want to see a copy of Zn, inside of the ring R, which is really going to take place for this piece here. I really want an NZ here, because then I'll know this whole piece, I know is ZN, and then I can see it as a copy living inside of my ring here. So this is really a subring of R. Okay, when my characteristic is 0, the goal is to show that this piece is isomorphic to Z, so that I have a copy inside of R that looks like Z. So what would I want my kernel to be in that second case? I want the whole thing to be Z. What can I mod out by? Just give me the same exact set. The trivial. So here, if this was 0, just if this was an injected map, then this whole quotient ring is the same as just my integers here. Just in the same way as if I modded out the whole ring, I would just be left with the trivial ring back out. Really modding out by 0, you're just saying 0 is the only thing that looks like 0 here, so it looks exactly the same. If my ideal was bigger, let's say the even integers, I'm saying all the evens really look like 0 here, and so I have 2 pieces showing up. Okay, so let's see what happens with our characteristics and make sure that it's actually what we want it to do. So if my characteristic is bigger than 0, then what I know is that the additive order of 1 had to be n. Because a ring with unity, we know exactly what its characteristic is, dependent just on the additive order of its unity. Okay, and so what this ends up doing here, say it again. If Z was isomorphic to R, then they would have the same characteristic, but we're not sure what the relationship is at the moment. So we can't say that they're going to have the same characteristic here.
So you are looking at
Okay, so here I'm looking at R. I want to decide how does the characteristic of R tell me about the copies that show up inside of it here. What does this tell me about the kernel that's showing up here? Because really the kernel will tell me the remainder of the pieces here. Okay, so here, if my characteristic, right, we said it was equal to n, what does that tell me about S? Does that give me any information about S? If I know my characteristic of R is n, so that's telling me that the additive order of 1 is equal to n. What does that tell me about my set S? It has exactly n elements. Right, because as soon as it gets to n, it gives me 0, and then it starts cycling back through the same exact elements that I had shown up here. So when my characteristic or my order of 1 is equal to n, S has exactly n elements. Okay, so putting this together, this is saying that Z mod the kernel is going to be isomorphic to something of size n. So what I have to mod out by needs to give me something on the left that has size n. The only ideal, right, because all of our kernels are really ideals of Z, that will do this is if this is equal to NZ itself. If this is NZ, then the left has size n. The whole thing on the left has size n. Bless you. Okay, so knowing the size of S gave us the size of our quotient ring. But because we have a lot of information about our ideals and the integers, we have to exactly know what that kernel had to have been to do this. So information about S gave me information about the quotient ring, which because this is so special, tells me exactly what the kernel is, and exactly tells me what this has to be. Right, so here the Z mod, the kernel is really Z mod NZ. which we know is isomorphic as rings to Z mod n. And now we're saying these two are isomorphic. So Z mod n is isomorphic to S. And this is just some subring in the ring, R. So I can really see the Zn as showing up in the copy as S inside of R. So I can really see here, when my characteristic is bigger than 0, R contains some copy of Zn, something isomorphic to Zn, which is going to be this set S. Okay, and then we're going to look at what happens when the characteristic is equal to 0. What does this tell me about the order of the unity? This is going to give me infinity. And we want to be careful here. This is one of the questions we had on the exam. And a lot of people said the additive order gave us back exactly the characteristic. But that's not true when the additive order is infinity. The characteristic is 0 here. Right. In terms of characteristic, our only options are 0 and then our positive integers. Okay, and so here, what does this tell me about S? It's going to be infinity here. So this is saying no matter which integer or really positive integer I choose, I'm never going to get 0 back out, and I'm never going to get repetition. So every time I choose a new positive integer, I'll get a new element back out. These are all going to be distinct, and I have infinitely many of these. So the size of S is going to be infinite here. Okay. Okay, so this is telling me that Z mod the kernel has to have the same size. And so I need to think, what ideal can I quotient out by to give me an infinite quotient right here? And again, my only options for ideals of Z are things that look like NZ, right? That could be 1Z or 0Z, which would give me all of the integers or just the trivial one. But those are the only options I have for my ideals of the integers. So what would the kernel have to be here? I only have one option that'll make this work. 0 or the trivial ring here. Right here, if I put 0, I'm really not taking anything away. I'm saying 0 is the only thing that looks like 0 now, so I should get the integers. Or I can see that as 0Z. And if I would have chosen any other number instead of 0, I would have gotten a finite answer back out, the size of whatever that number was here. So again, knowing information about the ideals of the integers is really giving us a lot of information on what the kernels would have to be in these cases. So here, the only options for my kernel is for it to be finite. And the only finite ideal I have for Z is going to be the trivial one. Okay, so this is telling me here that Z mod the kernel, which here we said was just the 0 element. But if I mod out by the 0 element, I just get the whole ring back out, is now going to be isomorphic to S, which is subring of the ring R. So now when characteristic is equal to 0 for R, I can find some copy of the integers living inside of it. Really something isomorphic to the integers living inside of it here. So that's really what my S is. In both cases, the S is the thing that we're studying. That's the thing that will be isomorphic to Z mod N, or the thing that will be isomorphic to Z here. But just knowing the characteristic of the ring tells us which one we should have a copy of inside of that ring here. So if I have characteristic 5 of a ring with unity, I know I need Z5 to show up in here. If I had characteristic 100, I know I have Z sub 100 as a subring or something isomorphic to it in the ring. This one's much simpler, and like one exact thing happening. If the characteristic is 0, I have to have Z showing up as a subring or something isomorphic to it. But it's important that it's a ring with unity. If it doesn't have unity, I can't apply this theorem, and I don't know what things I'll have showing up inside of my ring. But really all of our rings with unities are going to have one of these two copies showing up, either a Zn or a whole Z showing up. Okay. Our next corollary, really we have seen already, but here we have, oh, there's a typo. Let's see. I want this to be from Z to Z mod N. I don't know if I corrected this on yours, if there's this notation there, but it should be Z to Z mod N. And we actually studied this previously. We saw if we sent the integer to the class represented by it, so just mod it, and we'll get a ring homomorphism back out. But we can actually apply our theorem from above, where Z, right, we have as our domain, and the codomain needs to be something, a ring with unity. So our Zm here is that ring with unity. And this is the exact map that we had earlier, where we send an integer to the integer times 1, the unity, so add 1 to itself that number of times. These are really the same exact map. So here, this is the same as x being mapped to add 1 to itself that number of times, or just think of x mod n. Because these are the same, I can see that this will always give me back a ring homomorphism, but we actually proved this previously, that we showed that it did give us a ring homomorphism through showing all of the steps here. But with this theorem, it tells us it directly, because I started from Z and I went to a ring with unity under this specific map. I know I always will get a homomorphism. Okay, and the last one we have here for our corollaries is now going to be in terms of our field. So more specific than just a ring with unity. I now have a field, so I have a ring with unity, it's commutative, and all of the multiplicative inverses are inside of my ring here. I can also know, because I'm a field, I'm an integral domain, so I also know I don't have any zero divisors for free here. Okay, so if I start with the field, again, the characteristic is going to tell me the full story. So here we want to remember, even for integral domains as well, what are our options for characteristic? 0 or prime, we are seeing show up here. If my characteristic is prime, it turns out that I'll have a ZP showing up in my field. Notice that this is a field itself. Okay, if my characteristic is 0, then really I can think I'm going to have Z showing up in here. But even more than that, I'm going to have the smallest field that contains Z. And that's going to be the rational numbers. Really, the rational numbers, and we'll actually talk a little bit about this. All we did to the integers to give us the rational numbers is include its inverses. So things like 2, and I have 1/2. Things like 3, and I have 1/3 showing up in here. And I also want to make sure that inclusion under multiplication. This is why I get integers over integers with downstairs is not equal to 0. This is really telling me the smallest field that Z will be contained in. So this is how we'll think about how to split up the cases. We'll still think the last corollary that we had, but now we know we'll have a subfield showing up in there as well. And the subfield is going to be ZP or Q here, depending on the characteristic. Okay. So here, if we use our corollary 1, right, this is this one here. If our characteristic is equal to n, so if the characteristic of R does not equal 0, then it must be P for a prime P. Since our fields only have characteristics 0 or P here. Okay, and so this is telling me that I have a subfield. And earlier we just said subring. But here, because P is prime, we know ZP is prime. Isomorphic to ZP. So with the old corollary, I know because the number is P, that I'll have ZP sitting in it. Because P is prime, I actually do know it's a subfield and not just a subring here. So when my characteristic is equal to P, I see ZP living inside of that field here instead. Okay, and the one that's trickier that we won't go into full detail right here is going to be when our characteristic is not equal to 0. Oh, excuse me, when characteristic is equal to 0 here. Then by corollary 1 again, we have Z, the F contains a copy of Z. And isomorphic and the part that takes a lot more work is to show if you're a field that contains the integers, then you always have to contain the quotient, the rational numbers as well, right? You have to include the integers and all its inverses, and you need to make sure it's closed under the operation, so you have to have the rational numbers contained in it as well. But this takes quite a bit of work to actually show the rational numbers are really the smallest field that contain the integers. So any field that contains the integers also has to contain the rational numbers as well. We'd need to show that this implies that Q is a subfield of F, or it's isomorphic to a copy. Right, I have something in F that is isomorphic to my rational numbers here. Okay, but that part really does take quite a bit of work. And that'll show up in our fields of quotients, which is technically in this chapter. But there's like a page and a half of this in the textbook, not a lot of detail. I don't think that we're going to end up using much of it elsewhere. But I did make a packet for it. And now I'm kind of thinking maybe I'll just have this as like extra reading if you want to see in more detail what that would look like. And maybe I'll include like a bonus problem on the homework that's actually not that complicated, as incentive to kind of read through this and see where it's coming from. But it won't be necessary for the things we do, so we won't really go into detail about it there. But seeing how we can take a ring, and actually I need more than a ring. What type of ring is my integers here? An integral domain. So here really I need to be able to start with an integral domain, and I can always see it living inside some field. I can actually build what the field is. I can tell you exactly what it is. I'll build it for you. It might be hard for me to see what is that field in like regular context with like the sets that I'm used to seeing. But it turns out for my integers, if I want to build a field around it, it's going to give me back the rational numbers. In most other cases, it's actually really hard for me to see what will that be. Unless I start with the field already, it contains itself. So that would be the field of quotients that was showed up here. Okay, so here, even though the integers did not give us back, is not a field, it's an integral domain. It is contained in a field, the rational numbers, and really the rational numbers are the smallest field that contain it. Any field that contains the integers has to contain the rationals as well. Right, and we talked about how the rationals, really all we did is we took quotients of integers so that we could make sure that all the inverses were included, and so that it was closed under the operation, right? So that I can, after adding the inverses, I still need to be able to multiply my integers with these 1 over integers and land back inside my set. Right, but generally we can do this if we have an integral domain. We can build this field of quotients that contains the integral domain is a field, and it's the smallest field that contains it. Anything else that contains that integral domain and is a field has to include our field of quotients here. So really that's what this theorem is saying. If D is an integral domain, there's some field called the quotients of fields of D that contains a subring isomorphic to D. So I can see D as a copy inside of here. And so this is really how I can build my field around it to make sure I include just enough things to make it a field and nothing else, right? Because I could keep building and making more. I could have had the real numbers, right? That's bigger. It contains my integers and it's a field, but that's too much. I included too much stuff. I can find a field in between that contains my integers and is a field, which is exactly my rational numbers here. So I'll pass these out and I'll probably post like the filled out stuff for these. And there's only like one piece that I was probably gonna add to homework. And I think that I'll just make that as a bonus problem. Really checking what we would end up doing here is we'd come up with an equivalence relation to tell us what the new set would be and how to find an isomorphism to it that looks like our integral domain. But some of the things that we have to do there is make an addition and a multiplication show up in there. And I was just gonna have you guys check that it was well defined. And then maybe something like that the multiplication was actually commutative because we need it to be a field, so we need it to be commutative for both the operations there. So I'll pass these out. But if you don't read these, it's not going to hurt you. If you do, again, I'll post like the filled out notes for these. You can use some of the bonus problems that show up on the. These are pretty tricky, and I don't think the book does it justice. A lot of this is just like inside of a proof, and it just says check these things. So I did kind of help you kind of break it down to better understand it. Yeah, but we don't have to go into detail. And if you guys want, this also is good practice on some of your relation stuff, like checking if things are transitive or symmetric or transitive. Those kinds of things are showing up in here because we do talk about our equivalence relation here. Okay, so for Wednesday's class, again, you don't have to read this. It's okay if you don't get to it. Just it really is going to be helpful for bonus questions. Even in this section, there's not that many problems that are on this in particular. I might end up showing you one little piece of notation that you'll see at the end of the packet there. But again, I don't think it'll show up very often. So Wednesday's class, we should be able to start our polynomial rings. So our rings where the coefficients, or excuse me, our polynomials where the coefficients come from rings, and we'll build it from the ground up. Talk about like some properties that we should have seen previously, like things about the degrees of our polynomials, how to multiply or add them. Also, if I know my ring is an integral domain, what do I know about the polynomial ring that has it as its coefficients? But we can get a lot of information by just knowing what the coefficients are allowed to be here. But we'll go into a lot of detail for that on Wednesday's and Thursday's class. So if there are no questions, I'll see you guys then. Have a good one.